So how do we build a confidence interval for the mean when we actually know the standard deviation in the population? Imagine that you have a sample of n observations from the normal population, and you know that the population has variance sigma squared, but you do not know what the mean is. You don't know the mu. In fact, that's what you're trying to estimate. The sample mean x bar, which is just the sum of the n observations divided by n, the number of observations, that's a point estimate for the mean. The estimate isn't going to be exact, of course, because you could be somewhat unlucky with your observations, and if you try a different number of samples, you might get a different result for the sample mean, and if they're both different, they can't both be the exact value of mu, right? X bar, the one that you measure, is an observed value of the sample mean x bar. And it's very unlikely that it coincides with the true mean mu. It could happen, but it's unlikely. We know that if the observations come from a normal population, then the sample mean, according to the central limit theorem, follows exactly a normal distribution with mean mu and with variance sigma squared over n. If that's the case, we can standardize the sample mean by subtracting the true population mean mu and dividing by the standard deviation of the normal distribution that it follows. In this case, the square root of sigma squared divided by n, so sigma divided by square root of n, and that is going to follow a standard normal distribution. Now, for standard normal distributions, there's something called the 68, 96, and 99.7 rule. Roughly speaking, what it is saying is that if you go and compute the area between -1 and 1 for this expression here, the PDF of the standard normal, you're going to get approximately 68%, 68.3%. So this area here is about 68.3%. What this means is that on average, whenever you draw population from the standard normal, they will fall between -1 and 1 about 68.3% of the time. Well, if you're interested in knowing how often they would fall between -2 and 2, then you just compute the area underneath the curve between -2 and 2. This quantity here, it's about 95.5% or 96%. So 96% of the observations you would expect to be between -2 and 2 when you're drawing observations from a standard normal, and you do so independently. You can go even further if you want to figure out what percentage of the data should be between -3 and 3. Well, that would be this integral. That's about 99.7%. The overwhelming majority of observations you draw from a standard normal fall between -3 and 3. Now, how do we compute these numbers? How do we compute the probability that z falls between -1 and 1? Let me remind you, this is exactly the same as the probability that z will be smaller than 1, all of these points here, minus the probability that it's actually going to be all smaller than -1. And you get these values from the tables. Now this value here you will not be getting exactly or directly from the table, right? Because typically in your table this only works for thresholds that are between 0 and some large positive values, but you can obtain this quantity by noticing that the area here is exactly the same as the area here, right? These are symmetrical curves. So this area would be 1 minus the probability that z is smaller than 1. That's the same as the probability that z would be smaller than -1. And now, if you're trying to combine all of these together, you have the probability that z would be smaller than 1 minus the probability that it's smaller than -1. So that's the probability that it's smaller than 1 minus this thing here. What do you end up with? So you have a -1 and probability of z being smaller than 1, minus the probability of z being smaller than 1. So this would be twice the probability of z being smaller than 1 minus 1. And this value here, that's 68.3%. That's how you compute these things. Just a reminder, because it's been a while since we computed probabilities as areas underneath the standard normal. So this is sort of interesting. If you go one standard deviation away from the mean of a standard normal, you contain about 68.3% of the observations. If you go 2 standard deviations away from the mean in a standard normal, you get 95.5%, and 3 standard deviations away from the mean, you get 99.7%. Why do I say 1 standard deviation, 2 standard deviations, 3 standard deviations? Remember, in a normal distribution, which is standard, the mean is 0 and the variance is 1, which means that the standard deviation is 1 as well. It's a special case. So if I'm looking at what's happening between -1 and 1, this is really mu minus sigma, and this is mu plus sigma. In this specific case, mu is 0 and sigma is 1. As it happens, because if you have any normal distribution with mean mu and standard deviation sigma, you can standardize it so that you get a standard normal. Well, this relationship is going to hold for every normal distribution. In general, what you would write is that the probability that your value x or y or z or w or whatever is between mu minus sigma and mu plus sigma is about 68.3%. This is what I was talking about here. Whenever you observe a sample mean x bar from any normal population with mean mu, you would expect the inequality thing I've just described here, where k could be 1, 2, or 3, as in the previous example, to hold approximately 68.3% of the time, 95.5% of the time, and 99.7% of the time, depending on if it's 1, 2, or 3. Now, if you take this expression here and you solve for mu, the true mean that you're looking for, you're going to get a series of inequalities that we call the confidence interval for the mean. And it's a confidence interval that depends on the value of k, and the value of k gives you a difference confidence level. Depending on if it's 1, 2, or 3, you will be 68.3% confident, 95.5% confident, 99.7% confident. What is this really saying? It means that if you have a sample of observations, you compute the sample mean. You know what sigma is, that's part of the problem, right? We're assuming that we're computing the confidence interval for a normal population for which we know the standard deviation. We know the size of the sample, so we can compute the square root of n here, and we pick a k. We can pick 1, we can pick 2, we can pick 3, and there's a corresponding confidence level for these things. So let's say we pick k equals 1, then whatever value we've computed here for the sample mean, if we subtract the standard deviation sigma divided by the sample size, square root of the sample size, if we add it, we get a sandwich, and we have some confidence level that the true mu is somewhere in there, in that interval. And what's our confidence level? It's 68.3%. Right? So these numbers are easily computable from the sample, and that gives us an idea as to what the true mean could be. It's quite conceivable that the true mean would actually be outside of this. I mean, this isn't a huge amount of confidence, but there's still a fair probability that the true mean would be somewhere in the interval that we've built here. So as an example, let's say you take a sample of size 64 from some normal population, and you happen to know that this normal population has a standard deviation sigma 72. You don't know what the mean is. This is what you're trying to estimate. The sample mean gives you a point estimate for the mean of the normal population. And let's say that in this case, your 64 observations have a sample mean of 375.2. So if I'm asking you to build a symmetric 68.3% confidence interval for mu, you just need to find the k that corresponds to this confidence level? Well, the K that corresponds to 68.3% is 1. So then our confidence interval, our 68.3 confidence interval for mu would be the estimate x bar, which was 375.2, plus or minus K, which in this case is 1, times the standard deviation, which is known 72, and the square root of the number of observations n. And if you add these all up, you will get, if you start with the minus 366.2, if you use the plus 384.2. So that is your confidence interval for the true mean mu of the underlying normal population. And so you are 68.3% certain that the true mean is between 366.2 and 384.2, right? Actually, that's not what it means at all. When you say that you have built a 68.3% confidence interval, we're not saying that we're 68.3% confident that the true mean is between these two values. What this is really saying is that whenever you pick a sample of size 64 from a normal population that has a standard deviation of 72, and whenever you build a 68.3% confidence interval for mu, the true value will fall between whatever the endpoints of the interval are, about 68.3% of the time. Do you see the distinction? In this specific sample, the sample mean was 375.2, and this is what led us to have this specific interval here, right? So we had 375.2, and the two endpoints were at 384.2 and 366.2. And this distance here is just, well, K in this case, 1 times 72 divided by 64. K times sigma divided by square root of n. But if you were to pick a different sample than the one that I picked, your sample mean might not be 375.2, it might be 377.7, for instance. In which case, your confidence interval would not be 366.2 and 384.2. The center of it would have shifted. Now, it would have the same width as the one that I built, 72 divided by the square root of 64 times 1 for both of these sides, but it would have different endpoints. So what we're saying is that this procedure to build a confidence interval will yield intervals in which the true mean will be found 68.3% of the time. So it's not this specific interval which we are 68.3% certain will contain the actual true value of the mean. Here's an illustration. Rather than using a 68.3% confidence interval, we're talking about a 95% confidence interval. 95% confidence interval means that if you were to repeat the procedure where you pick the same number of observations for your sample from the same population, has the same standard deviation, and you build a confidence interval. So let's say there's 20 of us, and we each build a confidence interval based on the sample that we've observed, we would expect on average that the true value mu would fall within the confidence interval about 95% of the time. It doesn't mean that it's going to fall exactly into the interval we've built 95% of the time. So on average, this is what you would expect. You could imagine a setup where, twice out of 20 it didn't actually fall within the interval. It's sort of an accident of randomness. It depends on the sample that you've actually selected. But the one thing I want you to notice here is that every single confidence interval which is built from a different sample has the same width here, because the width doesn't depend on the sample, it only depends on the sample size and the underlying distribution. The position of the interval, the center of the interval, which is the sample mean, that depends on what sample you've selected. So if you had to build a 95.5 confidence interval for the same mean, the same sample, you'd use the same formula, you would just have a different K. Your K would be 2 instead of being 1. And this would build slightly different interval, 357.2 and 393.2. Well, all of these are built on the same sample mean, and so they'll be centered in the same location. Here's the original 68.3% confidence interval. Here's your 95.5% confidence interval. All you've done to go from the 68.3 to the 95.5 is increase the number of standard deviations that you're willing to consider. So it's always going to be the case that if the confidence level is higher, your interval is going to be larger. It's going to contain confidence intervals that are of a smaller confidence, assuming that you're working with the same sample. If you build a 68.3% confidence interval with one sample, and then you build a 95% confidence interval from another sample, it's possible that the 68.3% confidence interval would not be completely contained in the 95.5% because you would have a different central point if you have different samples. But if you're building them from the same sample, the 95.5% confidence interval will always contain a 68.5% confidence interval. And for the same reasons, you would expect that your 99.7% confidence interval would be even larger. Like if you think about what 99.7% means here, it means that if you were to run this experiment 1,000 times, if you were to pick a sample of size 64 1,000 times and build a confidence interval, then the true value for the mean would be found within the interval that you built about 997 times. That'd be 3 times on average where the confidence interval would not contain the mean. Now, given that you never know if the one you built is actually one of the 3 or one of the 997, you can't say that you are 99.7 certain that your interval contains the actual true mean. Now, instead of picking a fixed number of standard deviation away from the mean, you might decide to find specific values, specific critical points, which will guarantee, you might be interested in finding the points which will guarantee that the area underneath the curve is some value. The way we did it at first is we picked a specific value of z, -1, -2, -3, and 1, 2, 3, and then we computed the area underneath the curve afterwards, and we got these weird numbers. 68.3 is a bit weird, 95.5, 99.7. These are all sort of weird numbers. You could do it the other way around as well. You could say, find me the points which will guarantee that this is 95% of the area underneath the curve, or 90%, or 99%. So let's say you have a sample of n observations drawn from some underlying normal population. If you standardize the sample mean, subtract mu, divide by sigma over square root of n, you get that this is a normal distribution, which is standard, mean 0, standard deviation 1. And if you want to build a specific confidence interval, which will be 95%, you need to find the critical point z star, which will guarantee that the area underneath the curve between z star and minus z star is 0.95. Now we've computed that if you go between -2 and 2, you get an area under the curve of 95.5%. That's pretty darn close to 95. A little bit bigger than 95%, so we would expect that in order to get exactly 95, we would have to find some value here, which would be a little bit smaller than 2 and a little bit larger than -2. Let's see if we can find it. The expression on the left, as we've mentioned before, you can rewrite it using the commutative distribution function phi, for which we have values in the table, and you use the property of that function. Phi at minus z would be the same as 1 minus phi at z. That allows you to rewrite the probability that z falls between minus a critical point and the critical point as twice phi at z star minus 1. So you're looking for the specific z star, the specific critical point, which will guarantee that that probability, that area underneath the curve, is going to be 95%, 0.95. So solve phi at z star. You'll get that the critical point z star is such that phi at z star is equal to 0.95 plus 1 divided by 2. So here I just solved for phi at z star. And that value is the average between 0.95 and 1, that's 97.5%. So you look at your normal table and you find the value of z star for which phi at that value is 97.5% or close to it, and the closest value we can find is 1.96. So what this is saying is that the probability that z falls between minus 1.96 and 1.96 is approximately 95%, or if you'd rather, that the probability that the sample mean x bar minus 1.96, this critical point here, times the standard deviation divided by the sample size and square root, smaller than the true mean mu, which you're trying to find, and that's smaller than x bar plus 1.96. This value here times the standard deviation divided by square root of n, that should be about 95%. These are all things you can compute, right? You can compute x bar, it's the sample mean, you know what sigma is, you know what the square root of n is, you have 1.96, and that gives you a confidence interval for mu. Write it. This is your 95% confidence interval. X bar plus or minus 1.96, sigma divided by square root of n. If you're interested in finding the 99% confidence interval, you would play the same game, except instead of solving here for this being equal to 95%, you would solve for it being equal to 99%. You would find that the value that does the trick is 2.575. The confidence level that is of interest to you, we usually express it in terms of a small alpha value. So if we say that alpha is 0.05 or 5%, what it means is that we have a 95% confidence level. So whenever you see 1 minus alpha or alpha, keep in mind that we're usually talking about a small value of alpha. Now you can pick small values of alpha or large values of alpha and find the percentiles of your standard normal distribution. So roughly speaking, if you go to the previous table here, the Z alpha, which guarantees that the area to the right of the expression is exactly alpha, we call this the critical point. And if the alphas vary from 0.01 to 0.99, well, the corresponding Z alpha we call the 100 times 1 minus alpha percentile. So if you pick alpha, which is 50%, 0.5, you're going to be getting the median of your distribution, the 50th percentile. And if you pick an alpha of 0.25, you will get the third quartile. And if you pick an alpha of 0.75, you get the first quartile. So in general, when you're going to be building two-sided confidence intervals, later when we talk about hypothesis testing, we will see that it's possible that we're going to be interested in one-sided confidence intervals. But for now, we build two-sided confidence intervals. The appropriate numbers are found by solving this expression. And you play basically the same game as before. The standard normal has properties so that if you want alpha to be equal to the probability that the absolute value of Z is greater than the Z star, the critical point of interest, your percentile, if you want this probability here, right, if this is your Z star, you minus Z star, if Z is here, or potentially here, then Z is greater than Z star, so the absolute value of Z will be greater than Z star. And if it's a Z which is here, you would have that Z is smaller than minus Z star, so that if you multiply by minus 1, you would get that minus Z is greater than Z star, or an absolute value, because Z is negative, minus Z is the absolute value of Z. So you're interested in what's happening outside of this interval. By definition, this is going to be 1 minus the probability of being inside the interval, and then you apply the same properties of the standard normal. We've done this already 3 times in this video alone. This expression here is twice the CDF at Z star minus 1, and then you just work it out to get twice 1 minus phi at Z star. So that in general, phi at Z star would have to be equal to 1 minus alpha divided by 2, right? You want this probability here to be equal to alpha. And that means that the critical point in question would be the 100 1 minus alpha over 2 percentile. In other words, if you want this area here to be 95%, you don't have a choice. This has got to be 2.5%, and this has got to be 2.5%. So here alpha specifically was 5%. Alpha over 2 is 2.5%. 2.5%. These values here are important. We've already computed them. We know that Z at 0.025, the 2.5th percentile, or rather the 97.5th percentile, has to be 1.96. The 2.5th percentile would be minus 1.96. And what we get here is that the 0.5th percentile has to be 2.575. This corresponds to the 95% confidence interval. This one to the 99% confidence interval. So if you want to build something other than the 95% confidence interval or the 99% confidence interval, just plug the alpha in here that gives you the percentage you want, and then find the corresponding percentile, and you will get your confidence interval. If you're working with a confidence level alpha, remember alpha tends to be small here. So 95% confidence interval means that your confidence level is 5%. Shorter confidence intervals are better because if they're shorter, you have less leeway for the true mean to be in. So your estimates tend to become better when the sample size increases, because when n increases, then the square root of n increases, and then 1 over the square root of n decreases. So larger samples usually gives you tighter confidence interval. Another way in which you can have smaller confidence intervals, which would be better, would be for sigma to decrease. If sigma gets smaller and smaller, the expression sigma over square root of n will also be getting smaller and smaller. It will decrease, meaning that the full radius, which is some multiple of the percentile z alpha over 2, gets smaller and smaller as well. If the sample came from a normal population, this construction is exact. If it comes from some other population, but n is very large, then the central limit theorem kicks in, and what you get is an approximate confidence interval. Here's an example. You will pick a sample of 9 observations from a normal population. You know the standard deviation of this normal population, it is 5. And your sample of 9 observations gives you a sample mean x bar, which is 19.93. So what would be a 95% and a 99% confidence interval for the population mean mu, the true parameter, right? What we're saying here is that all of the xi's come from this distribution. You're trying to provide an estimate for the true population mu. Well, we've done this. Here we need to recognize what is the coefficient that we need if we have a 95% confidence interval and if we have a 99% confidence interval. And it's not a bad idea to remember those by heart. 95% is 1.96. 99% is 2.575. The only thing we need now is to identify the standard deviation. We know what it is. It's 5. The square root of n, well, we have 9 observations, so n is equal to 9. And the specific sample mean for that sample is 19.93. So all of the information is there. And we build a 95% confidence interval. 19.93 plus or minus 3.27. This is one way to write it, but if you want to see exactly what these intervals would be, 16.66 and 23.20. For the 99% confidence interval, you get the same center, a wider confidence interval, however, 15.64, 24.22, and because the underlying population is normal, these confidence intervals are exact, the true confidence interval. So if I was to repeat this procedure a number of times, I would get a different sample mean every time, but the width of my 95% confidence interval would always be the same. Twice 3.27, and if I was doing this very often, about 95% of the time, the true mean would be in the confidence interval that I built of width twice 3.27. And 99% of the time it would be in the confidence interval that I built of width 4.29. That's the twice times 4.29. That's the radius that is obtained in this specific example given the confidence level of interest, the standard deviation for the underlying population, and the sample size. Now let's say that you take a sample of 25 observations rather than a sample of 9 observations, and you are trying to build again a confidence interval for the sample mean, so the point estimate for the sample mean. In this case, let's say that it's still 19.93. So you've picked 25 observations instead of the 9 observations from before. It's a different sample, but by coincidence, you get exactly the same sample mean. You go through the same process to build a 95% and a 99% confidence interval. You will get different confidence intervals. The formulas are the same. The only thing that changes here is the size of the sample. So if you go back up a bit, you will see that it used to be an interval from 16.66 to 23.20 for the 95% confidence interval. Now it's 17.97, 21.89. That new confidence interval is tighter, and the same result also applies to the 99% confidence interval. Increasing the sample size has reduced the width of the confidence interval. It has tightened it. Let's say that you once again draw 25 observations from your normal population, but now the underlying standard deviation was known to be 10 instead of 5. And again, completely by coincidence, you get exactly the same sample mean, 19.93. There's no reason why that should happen in practice, but here it happened. What would be the 95% and the 99% confidence intervals? Again, the same formula, x bar plus or minus the percentile times the standard deviation divided by the square root of the sample size. Now what has changed is the standard deviation. We have a larger standard deviation, which means that we would expect the corresponding interval, 16.01, 23.85, to be wider than the one we had with a smaller standard deviation. 17.97, 21.89 is indeed tighter than the one we've computed for an underlying population, which has a larger variance, a larger standard deviation. So you can see how the confidence intervals are affected by alpha, n, and sigma, not by x bar. In this case, x bar was the same, but I've picked an x bar that was the same to make you see that what actually changes is the width, not the actual position.